All right. Okay, good afternoon, everybody. Thank you for those of you that have come all the way to Mowbray, brave enough to venture out on a Friday and come to the laboratory. Can assure you no animals will be hurt in this process. Um, but yeah, thank you for those of you that have come in person, and thank you to everybody that's joined online. We like to start strictly on time, and today's presentation is quite dense as I put the slides together this morning. I have given this presentation a few times at the Maritime Law Association before, but I realized that it's actually quite technically dense. So what I think I'm going to do is I'm first going to start with an introduction about the company and some of the work that we've done around legal matters. And then we'll get into the case studies. And after each case study, I think I will allow 5 minutes for questions. Because to go through all 3 case studies and then go back and ask questions about the first case study might be confusing. So please don't be shy at the break when we have the chance to do questions about the case study. Don't hold back. For those of you who are online, please ask your questions. Okay. All right. So 180 is a consulting engineering company, specifically in the space of materials engineering. And we are uniquely a consulting engineering company run by postgraduates and graduates engineers with an accredited testing laboratory to ISO 17025. This is in line with international standards and trends where these services are delivered as professional engineering services, including the accredited testing data that goes along with the consulting work. Okay, so materials engineering touches all fields of engineering. As you can understand, you can design a bridge, you can design an engine, you can design a pressure vessel, you can design a subsea structure, a wind farm, a solar plant. But at the end of the day, you've got to build it out of engineering materials. And when the failure happens in the material. And as much as we value the role of the mechanical engineers and the chemical engineers and all the other engineers who played a role, the interpreting the fracture surface and understanding how the materials respond to stress, corrosion, wind, whatever the case may be, is really what actually helps us get to the root cause of things. So that is why materials engineering is important. All right, so this is just a little graph to put materials engineering into perspective. So I've randomly selected material stiffness. The material stiffness is the resistance of a material to bend and flex, called Young's modulus, and that's on the y-axis, and the density of the material on the x-axis, okay? And this shows you the range of materials that we as engineers have at our disposal today. So it's not as though we can just build things out of steel. The steel is steel is steel, and all steels are the same. There are so many engineering materials that we have access to, and so many different types of engineering materials that this whole field has become an entire engineering discipline on its own. So 180, we are a group of metallurgical, materials, mechanical, graduate consulting engineers. We now have also adopted a few chemical engineers. We are supported with the SANAST accredited laboratory, which is also uniquely BV Marine and Offshore approved, which means that we meet the class requirements for classification societies under IACS. And we like to bring high-level technology to real-life problems. That's what makes me really excited and gets me out of bed in the morning and gets me to the office. So these are just our accreditations to take you through them. We've spoken about BV and SANAS. We're also a member of the South African Institute of Marine Engineers and Naval Architects and the South African Stainless Steel Development Association. And recently having conversations about joining the ladies in our office joining Worcester. So my vision is to be the Africa partner of choice that provides materials engineering solutions of today and tomorrow. So the rest of the world, America and Europe, is saturated with materials engineers. Companies like mine in America, for example, there are about 1,000 to 3,000 companies across the spectrum of employing 0 to 100 people or 100 to 10,000 people to companies listed on the stock exchange in America. So there are about 200 to 300,000 people like me operating in the United States of America. In Africa, there is not very much. And it's also a part of our conference is to create awareness and to build capacity within Africa. So my vision and my market is Africa. The other markets are saturated. There's no point in a company like me trying to compete with Exponent listed on the stock exchange in America. But Africa is what I have a vision for, and I love Africa. And it takes an African to grow an African business. Why choose 180? We say due to our integrity, our reliability, and effectiveness. I think most people that work with us find that that is the consistent experience that they have with us. Right. So before I get into the case studies, I wanted to just refer back to a presentation given by senior advocate Mike Ragg, very well known in the maritime space. If you need to win a matter, you speak to Mike. He's very well known, very experienced. And at the inaugural root cause analysis conference, he gave a lecture on the role of an expert in litigation. And I wanted to start with this because I think it's very important as I'm reviewing case studies that went to litigation, what the role of an expert is and how we approach expert witness work within this office. So just to summarize his presentation, which was 40 minutes long, the expert opinion must rest on facts and evidence as opposed to speculative or inadmissible foundations. The expert must demonstrate independence, resisting the pressures of litigation. There is transparency in how evidence is selected and evaluated, and that is where the accredited laboratory comes in. Where the testing is done by an accredited laboratory, we have to be impartial, we have to be neutral, we have to be objective. That's part of the accreditation. Cooking up experiments in your kitchen is just not good enough anymore. The expert must avoid undue alignment with the party that retained them by exhibiting bias, conflict of interest, or acting as an advocate. So I'm sure you've all worked with experts, the people that are sitting here, and it's also been our experience is that sometimes the expert starts to argue the case, and it's not for us to argue the case. I go so far as to say sometimes that I don't even want to know whether we are for the plaintiff or for the defendants. I just want to stick with the engineering. And if that suits them and they can use it, fantastic. If it doesn't, well, I'm here for the judge. I'm here to assist. And in fact, if there is no case, it's better that the parties find out before they start litigation. If you want to read more about his article, you can go to our website. We have an online magazine that we launched in July called MATERIALA Africa et al. Monthly. And this is part of our vision to grow awareness and understanding of materials engineering and how it intersects with insurance, legal, underwriting, and finance across Africa. Okay, so let's just want to review a few matters that I have been involved in. I counted on my CV, there's 24 since I started in 2002. But my first rodeo was with the MD Azure, the rudder fell off that you can see there at the back, that fell off. And that was my debut into the world of expert witness. I had no idea what I was doing. I was completely green. And I was lucky enough to be appointed by Craig Cunningham from Berman's. And he was very, very supportive and helpful, and he guided me along the way. And I learned a lot very, very quickly. Today, we're going to be looking at the brewery's failure of their heat exchangers, the fracture of a bollard on a fishing vessel, which resulted in a casualty, and a fire reticulation system, which rendered a fish processing plant uninsurable. I've also worked on the Margaret. Just put that there because everybody in South Africa has worked on the Margaret, so I've also worked on the Margaret. All right, I'll just take you through this very quickly. The range of matters that we have been involved in is quite diverse. So we've been involved in matters where people have been fined for various processes. So, for example, Casper, who are a foundry just down the road, were fined for manganese processes, which is associated with actually ball milling manganese ore, but they were actually putting manganese billets into the melt pot while making steel. So the person who came around to assess them did not understand what the processes were actually on the sheet. They just saw the word manganese and they saw manganese on the shelf and they said, oh, you're guilty of manganese processes. So it was very, very nice to be able to get this person's matter completely quashed. It was thrown out of court. And that was a very nice outcome. I've been involved with corroded structural members of buildings. It rendered the building had to be demolished. Wall paint, wallpaper, screeding tiles, thermally resistant materials. Marcel Deval does a lot of that work. Compliance of goods and materials for construction. We do a lot of that sort of work. Water reticulation pipes, whether they be galvanized sufficiently, so on. We're currently involved in desiccants that are used for containers on ships. We've done a lot of work on pressure vessels, in particular an isotainer that everybody in Cape Town has also worked on. And failed food and beverage equipment is a big problem in the Western Cape, especially when it results in the loss of large volumes of very valuable wine. So, and then we've also been involved in packaging failures such as cans, tins, and closures. Okay, so our range of consulting services covers all engineering materials in all industry sectors, which makes us a very robust service provider. Right, so let's get straight into case study number 1. This was a fire reticulation system at Sea Harvest in Saldanha Bay. It was the entire plant that had installed a 20 million rand fire reticulation system. After 6 months, it started to leak, and because it was leaking, it was contaminating the product. So they had to switch it off, drain the system, and therefore they could not be insured for fire, which was quite a problem for them. So they brought the some examples of the corroded pipes to me to start doing the root cause analysis. Since I've done this matter, I cannot walk into a building without looking at the fire reticulation system. Go into a car park, I immediately look up at the fire reticulation system, check my sanity, was I correct? And yeah, well, you don't see fire reticulation systems looking like this. If you go into a car park later today and have a look, they don't look like this, and they should definitely not look like that. But that is what every single pipe on that whole plant looked like. So our job was to figure out why this happened and who was to blame. So typically, this is what a installation will look like. And yeah, we were provided with a sample. What we did, so on the right-hand side is an electron microscope image of a sample that's been taken from the pipe. But now we needed to take a sample. There's no point in taking a sample in the corroded area because the damage has already been done. The corrosion obviously occurred because the paint coating failed. We had to get on top of why the paint coating failed. So we needed to see what the paint coating looked like in areas where it was still intact and follow the failure to where the paint started to peel off. So to do that, we mount the sample in a special type of resin, which has very good edge retention. We call it edge retention. And that means that it holds the paint coating and any contamination between the paint coating and the steel very tightly on a microscopic level. We then prepare the sample by grinding and polishing it, and then we take it to what we call an electron microscope. An electron microscope is an amazing high-level technology item to solve this real-world problem, and it uses electrons to create an image. So it scans the surface and creates an image. And what you're seeing here is a steel substrate. So it is a section through the pipe. If you can imagine this cut in half and then ground and polished, so you have the circumference of the pipe section, and then you can look at very high magnification. In this case, you can see that little micron marker there is 100 micron. And what you're seeing here, because we are using something called the backscatter electron detector, we are able to see contrast associated with composition. So iron seal will be bright because it's a big atom. It has a lot of electrons and it shoots out a lot of electrons when it's bombarded with electrons. Paint coatings, which are carbon-based, small atoms, don't have lots of electrons. When bombarded, don't send out a big signal. Right, so that's the basic principle. But what's very interesting is you can actually see a beautiful paint coating here covering small areas of rust. This over here is rust. The electron microscope also allows us to put the probe into the areas of interest and measure the elements that are present there. So we were able to confirm by first testing with a probe what was here in terms of the steel, and then putting the probe onto this contaminant here and seeing a change in iron levels and manganese levels, and we could conclude that that contaminant there was rust. Also, the nature of it and the appearance of it, it's not metallic anymore. It's become an oxide. And the only oxide it can become is Fe2O3. So essentially what has happened here is the contractor who installed these fire reticulation systems painted over rust. Now one would think, how on earth? I mean, why would anybody do that? Could that even be possible, and how could that be possible? Here's just another example where I've just boosted a bit of the brightness and contrast to show the paint coating very clearly, and it's the correct thickness and everything, and it's a completely a fantastic high quality coating. Unfortunately, underneath it is oxide, iron oxide, and here's the steel substrate. All right, so to understand why or how this could have happened, I consulted with both the NACE codes and the ISO codes. The NACE code is the National Association for Corrosion Engineers, and there's a matching ISO code, International Standards Organization code. And these codes define paint coating systems and how paint coating systems work. So if you use a particular type of paint, the standard will state what surface preparation needs to be applied before the paint coating is applied to that surface, and the period of time that is allowed between the surface preparation and the application of the paint. So paint is not just paint. Paint is both the paint and the surface prep together. So it's a paint coating system. In the case of the fire reticulation pipes, an alkyd paint was used. So that red paint that you see on fire reticulation systems is an alkyd paint. It's also the same type of paint they use in structural members inside buildings. It's the correct type of paint. It's the appropriate type of paint for the problem. But it does require what is called a commercial SSPC SP6 sandblasted surface. So that means that the pipes need to be sandblasted with a sandblasting gun before the paint coating is applied. And in fact, the paint coating needs to be applied within 2 hours after sandblasting, because otherwise rust just reforms. Okay, so here's a description. A commercial blast clean surface when viewed without magnification shall be free of all visible oil, grease, dust, mill scale, paint, oxides, corrosion products, etc., and so on. So that is the description of the SP6, which goes with the alkyd paint system. But clearly from the electron microscope images, that was not the case. So now you deliver a report like this because you don't have any further information, and sit down with the client, and the client says, well, actually, that makes sense because they delivered the pipes to site and they weren't painted. They left them there for 6 months in Saldanha Bay. And then they saw, when they came to install the fire reticulation system, they just used a bit of sandpaper to take off the rust and then painted them and installed them. I said, well, that's not an SP6 system. So thankfully, that came out very nicely during cross-examination in the court matter, and it seemed like a fairly open and shut case. So I'm going to stop there. I'll just say, while you're thinking of questions for that particular one, how do I go back? Okay. Yeah, the matter went to court. It was heard on its merits, and the other side didn't have an expert. And then they brought an expert in, and then suddenly everything changed, and suddenly it was okay to paint over rust and all of that. And that's how things go. But anyway, that was the root cause analysis that we did there. And if any of the attorneys that were involved in the matter online, maybe they could answer more the legal questions. Like I say, I like to stay out of the legal nuts and bolts and just provide the evidence. So any questions on the fire reticulation system? Please don't be shy for those of you online.
What we call it's okay to paint over rust. I always understood that encapsulates the rust, so it prevents oxygen from getting to firm. So, well, but the rust will still be there, but it will prevent further rust from form.
The problem that you had is that because you don't get a chemical bond between steel and the alkali hang foot, and due to the SK6 surface finish not being there, because the alkyd is then not able to actually chemically bond to the steel surface, you had those areas and they just chip off, they just flake off. Alkyd paint coating turn up a very robust protein. It's a very fragile protein. So and you can't remove all of the moisture out once you paint it. So there could be small amounts of moisture. The rust only needs to grow in volume by 1 or 2 or 3%, and then it will just pop off that part. Now you've got a small anode because you've got an exposed piece of steel, a very big cathode, which is the rest of the steel that's covered with paint, and then you get accelerated corrosion in those areas of the paint as plate. It's actually better to not paint all.
I just want to say, if I used in a studio the rate of cycle, it probably would have spotted us, but then it was never paint to use.
No, there is a varnish image. They talk about there being a de-rust paint.
Yes.
And I went into that in quite a lot of detail and did find that it wasn't appropriate for fire reticulate to rest. Yeah, the alkyd in the SB6 was extended for well in terms of the mace. Yeah.
Like this joke one.
Any questions online before we move on?
Hello, doctor. Can you hear me? This is Ines Waleta here from Great Break River.
Yes, welcome.
I'm glad to hear there's somebody else that always looks at pipes inside parking lots and buildings. If you were involved, well, I was involved in shipbuilding, and then the fire main system is usually the most important, because if you have a fire on the ship, you have nowhere to go. And also the protection of those pipes as well.
Absolutely. I've just done the Cape to St. Helena race, so I'm acutely aware of how vulnerable you are in the middle of the Atlantic Ocean.
Yes. Okay, I'm going to turn my mic down again if somebody else wants to ask something.
All right. If there are no further questions, I'm going to move on to the next one. So, just click for me. Okay. Okay. This one is a bit tech heavy, so I'm just warning you up front. The last one, I think, was, if you thought was tech heavy, not as tech heavy as this one is going to be, but the last one is also a bit lighter. So this resulted, in fact, in a casualty. It was a bollard that was on the dock at the Oceana facility in Stompiasvai. And the vessel was tied up alongside, and they were pumping fish from, wherever they contain the fish into the catchment area for processing. And in the process, the bollard fractured, and that resulted in the death of the chief engineer, which was quite tragic. The matter went to court because the wife of the chief engineer made a case against Oceana, and also the harbor or the quayside owner for damages. And so we needed to go into a proper root cause analysis to determine the cause of failure. Unfortunately, I only received the bollard 4 years or 5 years after the incident occurred, which is always very difficult, and had to work off fairly poor photographs from the surveyor that had been photocopied 10 times, and I'd gotten the 15th photocopy of his reports. But in any case, we got around it and we got to the root cause. So this was our approach. What does the fracture surface tell us about the failure? What were the load requirements for the bollard? What was the bollard made from? And what were the properties? And by looking at those items, finally came to the conclusion. So first of all, this was the photocopy of the photocopy of the photocopy of the fracture surface on the day of the incident. This is the image on the left-hand side. And what's very significant about this image is that the metallic fracture surface is still shiny. It says no corrosion on that fracture surface. And I'll come back to why that's important later. There was an allegation that this was a fatigue fracture. And if it was a fatigue fracture, in other words, a slow and insidious propagation of a crack over a long period of time, there would be corrosion on the surface of the fracture surface. But there wasn't. So this was a catastrophic failure that happened on the day, and the fracture surface was entirely metallic. Of course, the expert on the other side said, well, this is a bad image, you can't be 100% sure, and all the rest. But we managed to get around that. On the right-hand side is a scanning electron microscope image of the fracture surface after several years with corrosion on the surface, making it quite difficult to interpret. But nevertheless, it's abundantly clear from the granular form of the fracture surface that the fracture is a result of fast, fertile, catastrophic fracture. So it was an instantaneous fracture that occurred. It was not a time-based fracture. So what resulted in this instantaneous catastrophic fracture is the next question. So we went to the bollard microstructure. This is what the material looks like under the microscope. And the first thing we do as metallurgists is we like to cut everything in half. We want to figure out something, we cut it in half. So don't be disturbed by that. We won't cut through it half to figure you out. Yeah, we cut things in half, we grind them, polish them, and treat them with chemicals, and we can see the microstructure. And what we see here is these squiggly lines is called a flake graphite cast iron. The flakes are relatively large. Typically, we would consider that to be a problem in modern day cast iron making. And they are embedded in a matrix of ferrite and pearlite, which is completely normal. So the flakes are a bit of a red flag, not too much of a red flag, but a slight red flag. Not so great, but also not so bad. We then looked at the tensile properties, machined out a few tensile test specimens according to the standard core cast iron. And as you can see, we got an ultimate tensile strength. That means the load at which it fails at when you pull it apart. And what's important to notice is the strain to failure. So that's the amount at which you can pull it before it breaks. So a stainless steel, for example, will elongate by 20% before it fails. Aluminium, up to 40% before it fails. Normal carbon steel, anything from 10, 8, 15% before it fails. So a piece of steel that can only elongate by 2% maximum, and in some cases, 0.37%, means that there's absolutely no give in this material. It's not able to tolerate a load and absorb that load. Right. So that's a piece of information in the puzzle. The second piece of information in the puzzle is, well, we know we are looking at a fast, brittle fracture, a catastrophic fracture. So we need to look at the material's so-called fracture toughness. This is a material property that tells us the material's resistance to fast, brittle fracture. And it's measured as K1C or KQ here on the x-axis. And in highly technical units called megapascals, root meters. Don't be afraid. It's just engineering units. They won't kill you. And as you can see here, this is a graph for cast iron, and it typically shows you the sort of fracture toughness you can expect for cast irons with an ultimate tensile strength of between 140 and 260 MPa. This is a fairly modern graph. The bollard was installed in 1961. So not necessarily relevant to the bollard that actually failed, but this is the sort of fracture toughness properties you would expect today of cast irons if based on their UTS. We're clearly dealing with something that is outside of this range. Okay, so is that a problem? Well, we couldn't tell. The original drawings, which were hand drawings, blueprints, specified a 5-ton bollard on the quay side. So the question was it a 5-ton bollard? Yes, it was built in 1961. Was it a 5-ton bollard? Was it a bad bollard? Was it a fruit bollard? Was the stuff in the middle where you saw the fracture surface, did that weaken the bollard? All of these questions were coming up from the attorneys. So I consulted with the BA standard for maritime structures that deals with fenders, bollards, and fairleads, etc. It was first published in 1985 and revised in 1994. However, the bollard was manufactured in 1961. So the question was, did the bollard have to comply with BS 6349, or was the harbor master responsible to upgrade the bollard to comply with BS 6349? And in that case, were they responsible to make it comply with the 1994 revision or the 1985 revision? Or didn't it matter at all? These were things that were being discussed. Within BS 6349 are recommendations for bollard materials, which include cast iron, which is described in BS 1452. Okay. So with that in mind, I also decided to go and ask Google, what are bollards made of today? And then I phoned Trelleborg and Fendcare in the United States and asked them about bollards and bollard manufacturing and what are the typical things they see and failures that occur for them. And I got a lovely gentleman who'd been in the industry for many, many years. And he said, well, when was this bollard made? I said, well, 1961. He said, oh, well, in those days, you know what they used to do? They used to make engine blocks out of cast iron, and then all the dross and everything that was left over from making the engine blocks, they would just make it through bollards with the balance. And there weren't any standards for the bollards, and they were big and bulky and did their job. If you've ever gone to Cork Bay and kept a bollard, it doesn't fracture, right? So so he said that's probably what's happened here. You just got some, scrap cast iron that was made into a bollard in 1961. But again, was that really a problem? Because the specification on the drawing was that it needed to be a 5-ton bollard. So was it a 5-ton bollard or not? So I then looked into each of these standards and said, well, what are the specifications for grey cast iron in all of these modern day standards? And yes, the tested bollard did not comply with modern day standards for grey cast iron. However, did it have to comply? So then we went on into a different direction with this matter. We started to look at how the vessel was tied up alongside the quay. Okay, and as a sailor, and having been in boating since I was 5 years old, I know very well that you have a stern line, a headline, and you have two spring lines. And if you are able to, you have an offshore line. And this is the standard mooring arrangement in BS 6349, which looks quite normal to me and quite reasonable and rational to me. However, on the day of the failure, this was how the vessel was moored. There was a heavy surge coming through Stormness Bay. The chief and the skipper were under pressure to offload the fish and go back out to sea and fish some more. So they had taken the mooring lines and they'd racked them 5 or 6 times around the bollard of the vessel and the bollard of the quay. And the bollard that failed was the one in the spring area. That is its position. So essentially, each of those bollards were being heavily loaded by the fact that the mooring lines were tied around the bollard 3 or 4 times. We got into some highly technical issues around naval architecture and the vessel's equipment number and what the bollard rope sizes needed to be for the vessel's equipment number, and were the bollard ropes the right ropes for the vessel. We even tested the rope. Uncovered all of these things, but that would have made the presentation too long. The bottom line is they had the right ropes in the boats. They just wrapped them around the bollard too many times. So they basically made 5 breast lines, and they had no spring system. And the reason they did that is because there was so much surge, they couldn't keep the pump aligned to pump the products into the hopper. Right, so we did some finite elements analysis, and I have to acknowledge finite element analysis services is to Helmut Bowles, who did a dynamic analysis on the bollard on the day of the failure. So he models the normal arrangements, and he also models the actual arrangements on the day. So this required dynamic modeling, so the static analysis. You had to try and model the surge, the movements of the vessel up and down in 3 dimensions. So quite intense FEA modeling, and Helmut is definitely the person for that. And this was the result. The result came out that when first of all, the finite element model showed us that it was a 5-ton bollard. It would fail at 5 tons. If it was loaded in the way that it should have been moored, 5 tons would not have been applied to the bollard. When they loaded it in the way that they did on the day of failure, they applied over 5 tons to the bollard. So that was essentially the very simple outcome. So this mooring arrangement that was made up so that they could get the product off the vessel is what overloaded the bollard. The bollard was made in 1961. So the bottom line is, just because you're old, you're not useless. Okay, so the root cause analysis is that it was an overload. And in conclusion, the bollard was old but compliant with the code at the time. The bollard was a 5-ton bollard as per the drawing, and the bollard was overloaded by the mooring arrangements. Go back. Right, some questions on the bollard period, but that wasn't too deeply technical. Yes, Andrew.
Can you please explain what's the effect of wrapping it once or twice as opposed to wrapping it 5 times or whatever that they did? How does that affect?
So it's a stiffness issue. So if you wrap it once around, there's some stretch. The rope can stretch. So the minute you wrap it more than a few times around, you don't have that stretch, and that load is transferred to the bollard. Yeah, the rope is shorter, so but the boat should be able to move and move fore and aft and so on. But in this case, because the fuse became the bollard, the fuse should always see the rope. The rope should sail. Okay. But if you wrap it around so many times, you make the mooring line 5 times stronger, too strong to the bollard.
So it's still a single mooring line.
No, they wrapped it around it. They took it.
Oh, so it went from the bollard back to the boat, back to the bollard.
Back 5 times.
Oh, goodness. And I understand. Oh. I thought it was just wrapped around the actual bollard.
No. They went from the bollard on the quay to the bollard on the vessel to the bollard on the to the bollard to the vessel.
So it's like playing hanged.
And it was because they needed to keep the vessel, or to keep the pump aligned. With the surge, they could not keep the pump aligned, and they couldn't offload the catch.
What was the time of offloading, roughly?
I'm not too sure. But
Has the changing of the tide come into effect with the surge?
could have also, but it was a particularly strange weather condition on the day, which resulted in this particular surge that they didn't normally have, and they were under pressure to go back out because the catch was good. Any questions from our audience online, please?
Awesome. For the account of your key, are they also responsible for watching that ships not doing the right way? Or is it something else?
Yeah, so that was an argument, and one that I listened to from a distance about how if one party, so there was an attorney firm for the key side and there was an attorney firm for the vessel, and they had to admit a percentage blame. And I thought, how do you admit a percentage blame? 60, 40, 30, 70? But the minute one took blame, the other one was to blame. So even if they took 1% blame, to the other to say they were not to blame at all, or they were jointly. Yeah. So apparently the widow's attorney was quite clever, because by making the case against both parties, neither of them could get out, and it was impossible. They had to fight each other to get out. They had to settle with her and then fight each other to take from each other. So she was eventually paid out $4 million, Namibian dollars. So she applied for $8 million. It was in the news, so I can disclose that. Okay, I'm moving on to the heat exchanger at the SA Breweries in Newlands. Here you can see the heat exchanger that was taken out of service. The next picture is a bit better. And the heat exchanger is a tube heat exchanger, runs ammonia on the inside and water on the outside. But is it right? No, water on the inside, only on the outside. Sorry, I have to think about this. So yeah, I think it's ammonia on the inside and water on the outside. That would make sense because the galvanizing is there to prevent corrosion of the pipes on the outside. Right. So this is what the heat exchanger looked like. The reason it had been taken out of service is the brewery is in the middle of Newlands. And when they have an ammonia leakage, they have complaints from the residents because it smells like urine. And they also get into a lot of trouble. They're not allowed to leak ammonia into the atmosphere. So, from an environmental point of view, they're not allowed to do that, but also the people around, their house starts to smell like urine. So this heat exchanger just kept on leaking, and they took it out of service. They had 8 of these heat exchangers, and these heat exchangers controlled the brewing process. So if they had more than 2 out of circulation, they had to shut down the brewery. All 8 of them looked like this. Okay? So they were now managing which one was leaking more and keeping 6 out of 8 in service. They removed this one to do the root cause analysis to work out why the heat exchanger failed. Now, the first thing that happened is the manufacturer of the heat exchanger was present at the time of the inspection, and they said, "Oh, it's the water that the breweries uses from their spring, and it's the spring water that's rubbish, and it's put a whole lot of sand on the heat exchanger, and the heat exchanger is covered in sand. This is just sand because it's brown. It must be sand, and it's the water. The water is terrible. They don't do their water treatment properly, and that they destroyed the heat exchangers because of their water." And I looked at it as a metallurgist. I'm like, no, it's rusted. So apparently I had to prove that it was rust. So I had to take it off to the electron microscope and demonstrate that it was in fact iron oxide. This is what it should have looked like, the pipes, if they were galvanized. It was a galvanized heat exchanger. And so you can see how shiny and nice they should have looked, but that is what it actually looked like on the day of the inspection. I'm not going to get into how a heat exchanger works. But what we'll do is talk about how galvanizing works. So when the item is galvanized, it goes to the galvanizer, it stands outside for a couple of days, has no corrosion protection on it. That's all right. Rust a little bit. That's also all right. It's then placed into a acid bath, where the acid cleans off the rust and creates a nice substrate onto which the zinc then bonds. The problem is managing the acid baths is expensive. The acid has to be disposed of in an ethical way, and it's an expensive thing to do. So the galvanizers tend to run the acid bath to almost end of life and beyond end of life, where there's no more acid left to effectively clean the heat exchangers. Once the galvanizing, after the item has gone into the acid bath, it is then rinsed a few times, and then it goes into the molten zinc bath. So here you can see a staircase. being placed into a molten zinc bath. And here you can see a section, like we said, if you want to know what's wrong with something, we cut it in half. If you cut the galvanizing in half, you can see the mouse looking. Okay, so this is the steel substrate over here, and this is the galvanized layer. And what's important to know about galvanizing that many people don't know is that it's a metallurgical bond. There's actually an iron-rich layer over here, and a low level of zinc. And as you move from this layer to that layer, you get an increase in zinc and a decrease in iron. And each of these little phases in the zinc coating need to be present for the zinc coating to be effective. If the zinc coating doesn't form and look like that, the zinc coating will not be effective. Okay. All right, so I was first of all just appointed to test whether the stuff on the heat exchanger was rust or sand. And I took it off to the electron microscope and we found that it was rich in iron and therefore it was rust. It could be nothing else. Then they said, oh, well, you know, there was all this talk about, this was one of these failure investigations that happened in a piecemeal way, which is sometimes quite frustrating, but it's quite nice when it does eventually come together. Right, so then I got some water data from breweries. I got a lot of their data. I'm just putting one slide up to show you an example. And this is the specification that was given. And you can see that the water, there's really nothing wrong with the water. Chloride levels are quite normal. There's no specification for the chloride levels, but where there is specifications, the water is within range. Okay, here you can say, well, it's slightly acidic, but typically for all of the data that I looked at, the water was always around a pH of 7, and seldom the pH of lower than 7. All right, so now you've got the problem of a corroded heat exchanger. All the galvanizing has come off. How do you figure out what happened to the galvanizing? So you go on the hunt for some remaining galvanizing on the heat exchanger, which I found on the return ends, where the galvanizing was slightly thicker. I sectioned it, again, edge retention resin, drying polish, and this is a light microscope image showing the steel pipe and the zinc coating. I'm sure you can see that there's a lot wrong with that, right? We agree that there's a lot wrong with that zinc coating. Okay, first of all, it's cracked. Okay, it's cracked. The layers have not formed in a homogeneous manner. And it gets worse. If you look over here, it appears as though we have the same problem as the paint coating, where there is rust underneath the galvanizing. But that we can see with the electron microscope, which does not lie. And it doesn't take sides either in port matters. So here is the steel pipe. Here's the zinc coating. And again, using the backscatter detector that gives us a compositional contrast, we can see the under galvanizing rust. And there were many images like that. Okay, so then they said, well, the manufacturer determined to prove that it was brewery's fault. They said, no, well, forget about that. It's actually the reason that this all happened is the ammonia leaked up for some other reason, got into the water, changed the pH of the water all the way down to 14, and that would have taken the galvanizing off for 2 minutes. So I thought, well, this is really ridiculous. I went back to my office, did some calculations, and thought, well, let's try to model that scenario and see what we get. Okay, so the total mass of zinc on the heat exchanger is 372 kilograms. The volume, we calculated to be this amount. It was just easier to do volumetric calculations than mass calculations. The life cycle of the condenser should be about 15 years, which meant that you could only lose 5 micron per year of the galvanizing. Okay? At a pH of 15 or 14, the corrosion rate would be 5 times the pH of 8 to 9, which was a specified pH for the water. Okay, that means 25 microns per year, means 0.48 microns per week. So even at a pH of 14, where the water would be the most corrosive, the ammonia would have to be fully concentrated in that water for an entire year to take off all the galvanite. So, and you're not going to keep ammonia in the water for a whole year. It's not possible to keep it dissolved in the water and keep the pH down to 14. The breweries would notice that the ammonia was disappearing all the time, and the neighbors would be complaining. So it was just a totally ridiculous scenario. So we went back to the galvanizing, and after shutting down almost every single counter argument, the sand in the feed water was excluded, water treatment was excluded, the effect of ammonia on the feed water was excluded, and per sample preparation, of course, my samples that I prepared for electron microscopy were precise, and the features that I've observed in the prepared samples were attributed to the sample preparation itself, which was also not reasonable because there are standards on how to prepare samples with coatings and failed coatings, which we follow. So as an accredited lab. So in conclusion, the galvanizing was incorrectly applied to a rusted surface, which resulted in premature flaking and failure. The outcome, all 8 heat exchangers were replaced at no cost to SA breweries. I think that's a pretty solid, sorry, let me go back. A pretty solid outcome for the clients. Any questions? Yes, Andrew.
What exactly does the acid do to the rust when you wash? You said you wash off the rust.
Yeah, it will dissolve the iron oxide.
Does it create a coating?
No.
So just dissolve the iron oxide and
And even take a layer of the steel or strip a layer of the steel so that the steel's completely pure iron without any contamination. And it's rinse and goes immediately into the bath. Okay, any questions from the audience? Online?
Tinus Volity here again.
Yes, Sennis.
It's interesting to see those micrographs of the galvanized coating, but I never knew it actually interfaces with the metal surface. It's not like hot dip galvanizing in the previous century. I think these are more sophisticated galvanizing.
As it always has been, the process has always been to first keen with acid and then hot dip galvanize. And that's the reason that you can, even with like thin plates and strip that's been galvanized, that you can form it into shape. You can make channel sections and things like that because it is a metallurgical bond and it's able to actually strain. That's the purpose. It has to be a metallurgical bond. So there's actually diffusion of the zinc into the iron and the iron into the zinc. And that interface is actually an alloy. That's what makes galvanizing successful. And if that alloy doesn't develop at the surface, the galvanizing is set for failure.
Thank you.
Okay, no problem. Any
Hi, Janet. And Antonio here online. I had a question, sorry for missing the first half of the presentation, but I mean, this example sort of for me spells out in rands and cents the case for understanding, getting to the bottom of things, and basically a principle of root cause analysis. Can you maybe just explain to me and others what the connection between, say, a 3.2 test is and these sort of more technical tests that you've been conducting, just so that I can understand how they work with each other? Thanks.
Yes, thank you. Just by way of introduction, Antonio is our conference director for the Root Cause Analysis Africa event, and I'm going to put on a slide just now and hand the floor over to him. But that's a very good question, Antonio. We have a client called Lindsay Africa who make farming equipment, and they rely on galvanizing for their corrosion protection. And they had a failed galvanizing system and had to do a total recall. As a result of that, they now leave a coupon with every batch of galvanizing that they do, and they send that coupon to us as a so-called or type of 3.2 a third-party inspection of the galvanizing quality before they release payment to the supplier to ensure that they don't have to recall and get a reduced life cycle out of their farming equipment. So I hope that answers your question. All right, so go to the next slide. All right, so I'm just going to quickly introduce this, and then Antonio can tell you a bit more. I'm going to take the opportunity to tell the audience of our second Root Cause Africa conference being held on the 10th and the 11th of March, which is straight after the mining Indaba, on the Tuesday and the Wednesday of the week after the mining Indaba. And this is a curated Pan-African event to build local capital of expertise for the sustainability of the industrialization of Africa. I've just been to the Africa Energy Week, and there is aggressive strategies for growth in Africa and oil and gas and infrastructure projects. And with a lack of materials engineering expertise, we don't want another Medupi and Sile to be pillars of and reminders of what happens when materials engineering doesn't exist. But Antonio, perhaps maybe I can give the floor to you now.
Thanks, Janet, and greetings, everyone. Apologies for being late. So basically, what we are really aiming to do at the conference is bring together the various stakeholder groups that I'm sure Janet had mentioned. Number one, the producers, particularly in the energy and mining space, but also food and beverage. Basically, any industry that works with metals, metallurgical structure. And the insurers, the underwriters, the financial service providers, and the legal experts, those stakeholder groups who are normally brought together during times of crisis, once an industrial accident has happened, and are forced to speak to each other under times of crisis, and where there's a lot of sort of a searching for blame, liability, responsibility, and to really turn that equation on its head, bring together those stakeholder groups during times of peace, so that, or so-called peace and preparedness, so that the various professions can speak to each other, learn from each other. And what we really want to do is provide an opportunity for underwriters and the insurance community to learn from the engineers, to write more informed claims, to be better informed in terms of underwriting, for the legal experts to also provide their input and learn from the engineers and the insurance partners. Really, as Janet had referenced earlier, when we look at industrialization in Europe and North America, the concept of root cause analysis is well integrated, it's well mainstreamed into the costing of insurance underwriting, ex ante, before production, anything goes into production. And what we're wanting to do is grow that culture across Africa, to make sure that plans and substances, the materials engineering is sufficiently tested, so that we conduct the root cause investigations before things go into production, ensuring safety, more cost-effective claims, and avoiding accidents where we can. So that's what we're trying to create in March next year, in the Winelands area, as Janet said, 10th and 11th of March, at the Asara Wine Estate. We're hoping to have many people from the mining Indaba come and learn and see how we can really change that culture and have something that is an industry that is as de-risked as possible. So that's the gist of it. I'll hand back to Janet if she has anything to add, or if there are any questions, I'd be happy to take those. Over to you, Janet.
The case studies that I presented today were quite tech heavy and quite legal heavy, but I hope that it does show the unique intersection that materials engineering has with the legal industry, which is often triggered by an insurance claim, which affects an underwriter's pockets or affects a financier's pockets. He had another example at the inaugural events on how a 90 Rand elbow joint costs an underwriter 500 million Rands. Nobody bothered to test the 90 Rand elbow joints because they were only worth 90 Rand and there were only 1,000 of them. However, when the plant was commissioned and the cooling system was pressurized, all the elbow joints popped, they failed, and the project was delivered late. The client had a late delivery policy, and the underwriter had to pay out 500 million Rand. So those elbow joints that they were subjected to a 3.2 inspection, which seemingly would be insignificant over a 90 Rand elbow joint, would have prevented that payout. And it's those connections and intersections and dots that we want to join with the conference. With that, I conclude my presentation today. And if there's any more questions about the case studies or the conference, Antonio and I are here, so please ask away.
Thank you very much for the presentation, Doc. It was very formative.
Thank you. Thank you. What did you enjoy about it?
It brought back a lot of memories from the building days and the days at Benel, lots of disputes, big failures. So, thank you very much. On which a good word.
So what is your key takeaway today? What could you share with us as your key takeaway for the industry? What would you say to the listeners and the industry from this presentation?
If the contract pulls up certain standards or codes, better apply those and sticks to the rules. Otherwise, you could pick up problems afterwards. It's usually much more expensive to repair afterwards than we get right the first time.
Exactly. And in some instances, it's not even possible to repair. If we look at Medupi and Kusile, they will never produce the power that they were designed to produce. And that's something South Africa had to live with, and every single South African was affected by for many years. So, yes, we need to do things properly, and we need to do them properly the first time. So thank you for that.
Okay, pleasure. Have a good weekend.
You too. Thank you, Tennis. Any other questions from the audience online? Questions from the in-house audience? Is it 1 o'clock? It's Cape Town. It's 4 o'clock. It's Friday. I think it's 1 o'clock. Okay. Thank you, everybody. Thank you for listening. And this video again will be recorded and posted on the website under free seminars. Please also have a look at our online magazine where we now have 4 issues, and we discuss legal issues and insurance issues. We have several case studies and highlight tests of the month and materials innovations of the month. So please go to our website, have a look at that, and you can also see past seminars, which are the videos are also there, and the slides. This one will be posted in a week or so. Thank you very much. Okay, I'm out.